Hello, MacHacks, and we are Denatured. Our team chose to tackle the Inviand challenge and use deep neural networks to correctly assign the first enzyme commission number with an accuracy of 79%. My name is Daniel, and I worked alongside Aaron Lee and Isabel Regani to produce our hack, Denatured.
We made use of Google Colab to run our model using the NVIDIA Tesla K80 GPU. This was incredibly useful as without the GPU, our model would have taken several hours to fit. With the use of Google Colab's GPU acceleration, we were able to do this in a matter of minutes. We created a recurrent neural network and fit the model using TensorFlow Keras. We made use of GitHub to house our final model and the associated files. The first step is translating the given chemical information in the training data CSV files to a readable numerical format. We cleaned up the data and removed the characters which were not part of the molecules. Next, we separated each reaction into individual molecules. The molecules were then tokenized for relevant chemical features. We used Smiles pair encoding to do this. Smiles PE learns the vocabulary of Smiles substrings from the CH-EMBL dataset. The smiles are then tokenized based on the learned vocabulary for the deep learning models. The tokenization is inspired by byte pair encoding that is utilized by natural language processing. It is able to recognize recurring subunits across databases that may be of importance. Next, these tokens are assigned unique IDs using a dictionary so that they can be input into our model. Each reaction is input as a series of tokens.
For our model, we chose to use a long short-term memory, or LSTM, artificial recurrent neural network to train our classifier. We chose to use a LSTM because of its recurrent nature. It is well suited for natural language processing tasks due to its ability to consider previous inputs and outputs. In particular, an LSTM model was chosen because it addresses the vanishing gradient problem that's encountered in basic RNNs. A model was used to predict the class of the enzyme, or the first EC number. The training set was then split by the main class of each reaction, and 7 subclass models were trained to predict the subclasses. When evaluating the models, the main model first predicted the class of the reaction, and the reaction was then fed into the corresponding submodel to determine the second EC number.
Now that we've talked about our strategy for our model, let's evaluate its performance. For the first EC number level scores, we have an accuracy of 79%, a precision of 88%, and an F1 score of 88%. For the second EC number level scores, we have an accuracy of 55%, a precision of 48%, and an F1 score of 50%.
Given our evaluation of the performance, we can see that there are certain limitations to our model. So firstly, one of the limitations of our model is that it's trained on an unbalanced training set. As shown in the graph, there is a larger number of training cases for EC classes 1 through 3. Ideally, we would balance the test cases to cover all possible combinations in equal amounts. Secondly, our model does not differentiate if a feature is from a reactant or a product in the tokenized form. This leads to a loss of information for the machine when trying to predict what kind of reactants or products will be seen in a type of reaction. And lastly, while the training dataset for the tokenizer is very large, the model itself only uses and recognizes tokens that were present in the training set. When encountering a new token in the test set, the model is not able to quantize it. This was dealt with by removing the novel token. However, this is still a loss of information and something that should be addressed in the future. No model is perfect, and we should constantly strive to improve. We have outlined our next steps for the improvement of Denatured. Firstly, while a dataset of about 35,000 cases is impressive, increasing our dataset to cover more inputs and subclasses of EC numbers would result in a better trained model. Secondly, for architecture, we used an LSTM RNN. A different approach would be to use a transformer, which is a new deep learning model primarily used in the field of natural language processing. The transformer demonstrates self-attention and is able to weight the significance of different parts of the data that is input. RNNs and transformers both handle sequential input data. However, in contrast to RNNs, transformers do not always process the data in that order. This mechanism allows for relating different positions of a sequence in order to compute an overall representation of the sequence. This may help the model uncover additional patterns or features in reactions to better classify the EC number.
This was our first time making a deep learning model. It was exciting to see everything come together. We hope you enjoyed learning about our hack as much as we did creating our solution. Thank you.